preparation of alkenes, there are specifically 4 methods which are there in NCERT, and you need to memorize these 4. So I always say you should remember how many preparation methods are there for alkane, for alkene, how many reactions are there for alkanes, for alkenes, like that, or for alkynes also. That will help you to recall. 4 here: from alkynes, from alkyl halides, from vicinal dihalide, and from alcohols by acidic dehydration. In this case, the 4th one is specifically important because you will be using it multiple times in conversions. Okay? And the 3rd one also is specific to alkenes. So you should be very much familiar about the vicinal dihalides and how we prepare alkenes from vicinal dihalides. Last 2, 3, and 4 will be used in conversions. Say from alkynes, basically you have done a part of it. If you remember, we talked about that when alkenes react, okay, with the hydrogen in presence of palladium, nickel, etc., they get reduced to alkanes. Okay, so with that knowledge, you can say that triple bond, what we talked about, that double bond gets converted to single bond when we use palladium, platinum, nickel. Okay, along with, obviously, we get it reacted with hydrogen. And also we talked about, if you remember, from alkynes also, then we used 2s2. I hope you are able to recall that. I emphasize here 2s2 because 2 pi bonds will be broken in that case. Same logic we are applying here, but the problem is this triple bond can get reduced to alkene, which obviously we need. We are talking about alkenes, we are preparing alkene, but again this reaction will take place. So again this alkene will get converted to alkane, right? So we need to stop it here. Means it does not produce, or it does not proceed after this one. So for that, what we do, the reactions are very much similar. What we talked about in case of alkene to alkanes, alkynes to alkenes, it is very much similar. We are using hydrogen, palladium with carbon, or we can use hydrogen, obviously reduction we are doing with sodium and liquid ammonia. Now you can see the difference, okay? You can see the difference. When you use palladium and carbon, we get cis form of alkene. When you use sodium and liquid ammonia, you get trans form. So this is something you will memorize. Normal, what we have done in case of getting alkanes from alkenes, preparation method, alkenes reduction, okay? Sabatiya and Sanderson's reduction, if you remember, okay? In that case, we talked about that hydrogen with palladium, platinum, nickel will give you alkane. Here we have alkyne, alkynes will give you alkene. Now there is a possibility that further it can react because hydrogen is available. This can further react with hydrogen and can produce R, is there, CH2, and then CR dash, R dash are alkyl group, and H2, okay? This H2 is actually, you can say 2 hydrogens, okay? So it can get converted to alkane. So we need to stop it here. For that, we use Lindlar's catalyst. Okay, I guess probably it is not written in NCERT. So just write it, okay? It is called, we use Lindlar's catalyst. Catalyst. Okay. And this Lindlar catalyst is actually catalyst poisoned with some component. Poisoned means it stops further reduction. That's why we call it poison. So we use Lindlar's catalyst, we use palladium as catalyst, okay, with calcium carbonate. So this part acts as catalyst. Then we can use lead oxide, okay, PbO2. This acts as poison. Means, specifically if you are preparing for NEET and IIT, you must be aware of it. Its function is that it will stop further reduction. So alkene will be reduced to, sorry, alkyne will be reduced to alkene, and alkene will further be reduced to alkane by hydrogen in presence of palladium. So we want to stop it here because we want to produce alkene. Okay. I will be repeating it again and again. Okay. Ariman. So what you do for that, you use Lindlar's catalyst. So a Lindlar's catalyst is a combination of catalyst part. Catalyst part means it will increase the rate of reaction. Okay. So its function is just to increase the rate of reaction. It cannot control whether alkene or alkane will be produced or not. For controlling that alkane should not be produced, poison is used. This is poison. And this whole is known as Lindlar's catalyst. So Lindlar's catalyst is whole thing. You don't need to write it. You just need to write Lindlar's catalyst. You just need to know. Now, it is not that only this Lindlar's catalyst can be used. We can use lead with calcium carbonate poisoned with quinoline or quinoline. Okay, quinoline, you don't need to remember the structure. Just for your reference, the structure is like this. Nitrogen is there. Okay, one nitrogen is there. Two benzene rings, you can say, but you know this is not complete benzene ring. There is a nitrogen here. This is known as quinoline. Quinoline. This has same function. Here, this is catalyst part first, and quinoline is poison. Okay. Just a second. Just give me a few seconds. Let me see why it's slow here. Just a second. Right. So any confusion here? What we can use? Okay. Now you might see it. You should know all the possibilities, right? I hope you have noted it down. You might see written as lead plus BaSO4 also. This also does the same thing. Lead plus BaSO4 will act as catalyst as well as poison. So this is another possibility. Another possibility is instead of this thing, you can get nickel boride. Nickel boride also. This is, no, this is not Pb, okay, palladium. This is Pd, okay, not Pb. So this is palladium and barium sulfate. Any can be used. Palladium plus CaCO3 plus PbO2, which is obviously, this is called Lindlar's catalyst. Okay. Or you can use palladium with calcium carbonate with quinoline or quinoline. Okay. So all these 4-5 possibilities you should remember. Then important point, when you use palladium with carbon, you get cis, or palladium with Lindlar's catalyst. Okay, so if you use Lindlar's catalyst, you will get cis form. If you use sodium with liquid ammonia, trans form. Okay, very important point. Normally students lose marks here. Directly, indirectly, it can be asked. Okay. Similarly, if you have ethyne, you will get ethene. So the triple bond will get converted to double bond. In this case, there is nothing like cis and trans, right? Nothing like cis and trans, because you can't have two on same side, two on opposite side. Remember the trick. The trick is, if you have on any carbon of the double bond, suppose this is the double bond. If you have two same groups attached, so here you have CH2, it can never show cis and transform, means it cannot show geometrical isomerism. The reason is very simple. If it has same ligands, we call these ligands. Okay? And suppose here you have CH3, C2H5. Here you have different attached. But you can't have cis and transform, because here you have CH3 and hydrogen. And here you have C2H5 and hydrogen. If you interchange these two, nothing is going to change. Okay? It is same thing. If you interchange these two, even then it is same thing, because even then C2H5 will be with hydrogen, CH3 will be hydrogen. So no change will be there. So if you have any two, okay, ligands same on carbon, it cannot show geometrical isomerism. That is, it cannot have cis and trans forms. Any confusion here, anyone? Right. So in this case, whether you use palladium carbon, whether you use Lindlar's catalyst, whether you use sodium and liquid ammonia, the product will be same. There is no cis and transform. Now here you have propine. This is propine. Triple bond, 3 carbons, triple bond, propine. It will give you propene. Okay. It will give you propene. This triple bond gets converted to double bond. Now the question, there's a question. Yes. Will propene obtained in previous step show geometrical isomerism? Tell your answer in chat box. Write your answer with reason. The question is, will propene obtained in previous step show geometrical isomerism? If yes, then why? If no, write your answer with reason. I want to know how many of you are listening to me. Okay. Mahi, Rida, Tulika, switch on your videos, everyone. Saptarshi, Pranit. This topic is such a topic that even if you don't know anything, you can do it. Okay, now I got few answers. Okay. Rida, correct. Tell me the reason. I asked reason as well. Tulika, answer correct, but reason not correct. Ariman, answer wrong. Shambhavi, answer correct, but reason is not there. Sayak, answer correct, reason is not there. Swayam, correct answer, reason is not there. Aditya, correct answer, reason you need to give. Ariman, okay, obviously it is, if it is not yes, it will be no. If it is not no, it will be yes. So there is no need to give the second answer here. Pranit, no, Pranit. Actually, double bond will show the geometrical isomerism. Geometrical isomerism will be in alkenes. Geometrical isomerism is a phenomenon of alkenes. In alkenes, you can have on the same side and opposite side the ligands. Bhavya, no, that is not the answer. Rohan, no, that's not correct. Saptarshi, answer correct, but reason not given. Aniruddha, incorrect answer. Rida, no, that's not the reason. Mahi, okay, now at last Mahi gave me correct answer. Only one correct answer. And basically I explained few minutes back. And I said, if you have two hydrogens on same carbon or two any elements on one carbon, it cannot show cis and transforms. It cannot show geometrical isomerism. Okay? I explained it. So you apply the same logic here. You have the double bond here on double bond carbons, these are two doubly bonded carbons which will be responsible for cis and trans form. So what was cis and trans form? Cis form was, if you have, I'm giving you just example, okay? If you have methyl groups suppose attached and those are opposite, it is trans form, okay? This is trans form. The same groups are opposite to each other. So this is trans form. Cis form will be that you have same groups on same side. This will be cis form. It will not be possible if you have two hydrogens on same carbon of the double bond. So that was the question. Simply, the answer is no. One of the carbon atoms attached to double bond has two identical CH bonds. It is not possible to have cis and trans forms. No geometrical isomerism. Okay, so that is the geometrical isomerism. Aryan, geometrical isomerism is that it should have cis and trans forms. Okay, so I just explained what is cis form, what is trans form. Cis form is that you have same ligands on same side. Okay, here you can have CS3 or you can have C2H5. You can have CS3, but on one should be same side. And remember, it is not necessarily hydrogen. It can be chlorine, but those are on same side of the double bond, either upper side or lower side. This will be cis form. And with the same molecule, if you have these chlorines opposite side and CS3 and obviously C2H5 will be now here. So now chlorines are on opposite side. This is called trans form. So if a molecule can be written as cis and trans form, can show cis and trans form, that will show geometrical isomerism. So in this case, it will not be possible because this carbon has two hydrogens, similar hydrogens. So you can't say whether these two hydrogens will be opposite or same side. Next, from alkyl halides. Alkyl halides means you have R, alkyl group, and you have halide, chlorine, bromine, iodine. So this R can be methyl group, ethyl group, whatever you want. Now, this is a very important reaction, and there is such a specific name type of reaction here. So you should pay attention here why I have written alpha and beta. In this case, wherever, so try to understand what this alpha and beta means. In this case, the halogen is attached here. This is other than carbon and hydrogen. So whatever is other than carbon and hydrogen, that is of importance here to decide alpha and beta. This is attached to this carbon. So anything other than carbon and hydrogen attached to carbon decides which carbon is alpha carbon. So if the chlorine, say this X can be, this is halogen, this X is halogen. It can be chlorine, it can be bromine, it can be iodine. Normally, we don't do reactions with chlorine. And I have told you multiple times why. Because reactions with chlorine, alkyl chloride are violent. Okay, explosive type. We don't have a mechanism to control those reactions. So we avoid those reactions. So X can be chlorine, bromine, iodine. In that case, and the carbon to which this chlorine or bromine or iodine is attached, that is called alpha carbon. Okay. Alpha carbon. The carbon next to that one is called beta carbon. If there is another one next to that one, that will be called gamma carbon. Okay. So suppose you have carbon here, that will be called gamma carbon. Alpha, beta, gamma. Alpha will always be that carbon to which functional group is attached. Okay. Now come to the important point. What is actually happening here? We get alkyl halides reacted with alcoholic KOH. Alcoholic KOH means it is potassium hydroxide plus ethanol, alcohol. So we don't write C2H5OH. C2H5OH, obviously, we write when we discuss mechanism in 12th standard. Here you don't bother about it. Alcoholic KOH. What is the function of alcoholic KOH? And it is something you will write. You will write this statement, and it will be used extensively in conversions again and indirectly in multiple questions. Alcoholic KOH removes HX. that is HCl or HBr or HI from alkyl halides, from alkyl halides. You will read this statement 3-4 times. Quickly read it. Wherever you see alcoholic KOH and heat is written, this is first thing which should come in your mind. If it is alkyl halide, it will remove the hydrogen halide. So what will it will remove? It will remove this part, hydrogen and halogen. It will remove it. So if it will remove it, what will happen? There are 2 electrons here in this bond. There are 2 electrons in this bond. So if HX is removed, it will have a bond which will have 2 electrons. It means this part will be broken. Hydrogen and halogen will have 1 electron each. These 2 electrons remaining on carbons will form the double bond. So earlier here was single bond. Now here it is double bond. The reason is these 2 electrons will combine to form the pi bond. Any confusion here? What I am saying? I am repeating it. What's happening here? This bond breaks. These 2 bonds break because hydrogen and halogen will go away. 1 electron each will remain on carbon, and the other electrons will go with hydrogen and halogen. So hydrogen halide will be formed, which is not written. HX will be formed, HBr, HCl, HI will be formed accordingly, whatever we have here. And rest of the electrons will form the double. And that's what we need. We need alkene. Alkene means double bond. Now, another important point related to this particular reaction. What we are removing? We are removing hydrogen and halogen. That's why this reaction is known as dehydrohalogenation. Okay. So X can be chlorine, bromine, iodine. I told you it won't be fluoride. The reaction is an example of dehydrohalogenation. Why? Because D means removal. Removal of hydro means hydrogen part and halogen part also. That's why dehydrohalogenation. So this reaction might be asked just by the name. Give an example. What do you understand by dehydrohalogenation? Right? Give an example. Dehydrohalogenation is removal of hydrogen and halogen from a molecule. An example is alkyl halides. When reacted with alcoholic KOH, by dehydrohalogenation, they produce alkenes. This reaction is also an example of beta elimination reaction. Why? So whenever you see beta elimination reaction or gamma elimination reaction or alpha elimination reaction, it indicates from where hydrogen is removed. Okay, so this elimination actually is related to from where, what's happening, that this elimination is the location from where hydrogen is removed. So if hydrogen is removed from alpha carbon, it will be alpha elimination. If hydrogen is removed from beta carbon, beta elimination. If hydrogen is removed from gamma carbon, gamma elimination. Having said so, in your syllabus, it will be beta elimination. Okay. So you don't need to bother about alpha elimination, gamma elimination. It will be almost always 99.9% cases beta elimination. And beta elimination means the hydrogen will be removed from beta carbon. And you know what is beta carbon. It is the carbon adjacent to that carbon which has the non-carbon or hydrogen group. This carbon, alpha carbon, is that one which has halogen here. Adjacent carbon is beta. From there, now the rate, this question is asked, what will be the rate of reaction? So there are 2 possibilities. Okay, there are 2 possibilities. Alkyl halide, when you have RCl, suppose you have RCl, you can have RBr also. You can have RiOs. These are 3 possibilities because the reaction will be for chlorine, bromine, and iodine. These are 3 possibilities. Means One case will be rate of reaction when the alkyl group is same. Alkyl group is same. Then whether the reaction with chlorine will be faster or whether it will be with iodine faster, which one will be faster and why? Okay. So in this case, the reaction rate will be this one. Alkyl iodide will have fastest rate of reaction. So if I have iodine here, the rate of reaction will be fastest. And if I have chlorine here, the rate of reaction will be slowest. And there is a reason for that. The reason is, if I have C and Cl, I have C and Br. C, remember, I'm not writing the other bonds, I'm just writing this part, C, okay? C and I. Suppose carbon is this much big. When we move down the group, tell me, we talked about it in third chapter, the size increases or decreases. When we move down the group, the size of the atom will increase or decrease. Okay, Ariman, good. Rida, yes, good. The size of atom going down the group will increase or decrease. Yes, correct. Aniruddha, Aryan, Pranit, Sudhit, Satsarshi, good. It will increase, right? So that is the answer. So carbon, I have shown. Chlorine, say, will be this much. Bromine will be this much. Iodine will be this much. Now see the bond. Bond, okay? Bond length here will be this much. Bond length here will be this much. Bond length here will be this much. Center to center. Center to center. The smaller the bonds, stronger it is. So this is a smaller bond. That is, it is stronger. Stronger means difficult to break. Difficult to break. Here this is longest bond. So it is weakest bond. Longest bond. Weakest bond. Okay. Means the force of attraction will be less. The molecules, the atoms are not close. Here the atoms are very close to each other. So force of attraction will be higher. That's why bond is stronger. Here the force is not stronger because of size of iodine. They are not very close. The atoms are not very close. So this will break very easily. So the Ci bond, yes, Aryan, that's what we are talking about. So that's why this will be the weakest bond. Now, if it is weakest bond, it will break very easily and it will be most reactive, because in chemistry, the reactions are always breaking some bonds, formation of new bonds. That's in every reaction, that's what happens. Okay? Some bonds break and other bonds are produced. So in this case, the bond will be broken most easily. That's why it will react fastest. So iodide will react fastest, chlorine slowest. Now there is another possibility that halide is same. So I can have CH3, CH2, 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 CH. I can have CH3, CH2, CH, Cl, CH3. And I can have CH3, C, CH3, CH3, Cl. Remember, all are butyl chloride. All of these are butyl chloride. Formula C4H9Cl. There will be 4 carbons in each, 9 hydrogens, and 1 chlorine. These are isomers. But there are these different possibilities. And what are these possibilities? These possibilities are, I'm saying this is 1 degree, this is 2 degree, this is 3 degree. And I hope you remember what is 1 degree, 2 degree, 3 degree means. 1 degree is that carbon which is connected to only 1 carbon. So what I am considering those carbons only which are connected to chlorine. So now chlorine is same. Halogen is same. Alkyl group is different in this case, in second case. Then what will be the reactivity? 1 degree carbon means the carbon which is attached to chlorine is attached to only 1 carbon. That's why it is 1 degree. Now here the carbon which is attached to chlorine is attached to 1 and 2 other carbons. So it is 2 degree. Here the carbon which is attached to chlorine is attached to 1 to 3 other carbons. So that's why it is 3. Okay. In this case, the reactivity, which one, whether 1 degree, 2 degree, 3 degree, which one will be more reactive? This is the case. Tertiary will be most reactive, secondary will be less, and primary will be least. Now you might ask, or you might think that why tert is more reactive, why primary is least reactive. The reason is the reaction here will happen by breaking of this bond. Okay. When this bond will break, okay, what happens that this halogen takes the electron and we get this as cation. So when this breaks, okay, from here, what we will get? We will get CH, H, H, C, H, H, and positive charge. Okay. So if I write it the way I had written, CH3, CH2, 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 Cl, CH3, CH2, CH, Cl, CH3, then CH3, C, CH3, CH3, Cl. When chlorine will go away, this will be cation, this will be cation, this will be cation. This will be 1 degree cation, this will be 2 degree cation because it has 2 carbons attached to it. Okay, 1 carbon and 2 carbons attached to this one. The carbon which has positive charge is attached to 2 carbons, so it is 2 degree carbocation. And this is 3 degree carbocation because the carbon which has positive charge is connected to 3 carbons. And we know which carbocation is most stable. Tell me, out of 1 degree, 2 degree, 3 degree, which is most stable? Yes, Bhavya, good. Sudit, good. I'm asking some questions. You need to be active. Everyone has to be active in the chat window. Pranit, yes. Good. Only 3 answers. Bhavya, Sudhit, Pranit. Ariman also correct. And I also talked about, why. The reason also we talked about. Rida, yes, correct. Okay, so it's fine. 3 degree will be most stable. 3 degree carbocation will be most stable. Now, who intelligent student will tell me what I told you, why 3 degree will be most stable? I am waiting for intelligent answer here. Everyone. And I have discussed it at least, I think, 3 times. Why 3 degree carbocation will be most stable? Tulika, that's a good guess, but not the answer. Sudit, no. Aryan, yes, it is attached to 3 carbons. The question is why this will be most stable. Piranit, no, that's not the answer. Saptarshi, nope. Anirudh, nope. Rida, Rida, your statement is correct, but that's not a good answer. I can accept that answer at least, yes, Rida, but there's something else also. Aditya, no. Sudhit, no. Ariman, no, Ariman. From where do you get these type of ideas? I don't know. Okay, no. Okay, now when I tell you, you'll say, yeah, I recall it. Okay. Did we talk about hyperconjugation? Can you recall? If it is tert, how many possibilities are there that the sigma bond can be parallel to empty p orbital of C plus? how many possibilities are there that the sigma bond of CH, any CH3 can be in parallel to empty p orbital of C plus in third butyl. Now that's the problem, right? So there only one correct answer. Okay. Aryan, no. Only one correct answer. Only. So there, and this is something we have been talking about multiple times, right? There will be 9 such possibilities. It means you are not revising. Okay. There are 9 such possibilities because if you have carbon here and you have CH3 here, another CH3 here, another CH3 here. Now many students will recall because I am drawing the same diagram which I used to explain it. Okay. Now if this is the empty p orbital here, there are these 9 CH bonds, sigma bonds. Any one of these can be parallel to this one. Any one can be parallel to this. So suppose I say this bond is parallel to this one. So there will be some hyperconjugation, some electron sharing, which will make it more stable because this electron sharing will lead to some sort of bond formation, not complete bond, but maybe 25% bond. That will lead to stability. And because there are 9 such possibilities, so it will happen very quickly. That's why tertiary is most stable. In secondary, there won't be these many possibilities. Okay. In secondary, if you see here, you will have CH. Okay. And here you will have CH3, say for example. That makes it secondary. Only 2 carbons will be attached to it. Okay. So in this case, obviously only 5. Or if it is CH, say just H, maximum 6. If it is CH3, then only 5. 5 such possibilities, CH bonds, which can be parallel to this one, can lead to hyperconjugation. Okay. Yes, Aryan. Yes, correct. Okay, correct. So remember, in tertiary, there will be greater possibility of hyperconjugation. That's why tertiary carbocation is most stable. Now coming back to the question. Why? Now when we say this is most stable, then why I am saying that tertiary halides will be most reactive? The reason is, if product, here this is not product, but this is intermediate product. What's happening? Intermediate product. Okay, which obviously will be converted into some stable compounds. So first this will be converted to, if it is getting converted to stable tertiary carbocation, then this reaction will be very fast reaction, because the product which is being produced is very stable. Now suppose this product is being produced 1 degree, then this is not very stable. So if product is not very stable, the reaction will not happen very fast. So this reaction will be slow because the product being produced, which is being produced, is not very stable. So that's why, that is the reason tertiary will be fastest, because the intermediate product, the carbocation which will be produced, is very stable. In primary, the carbocation being produced in the middle of the reaction is not very stable, so the reaction will not be willing to proceed at faster rate. Any confusion here? Okay, I'm just emphasizing again and again few points which you must remember very frequently. These are asked in your exam and will be used in 12th very frequently. So don't take it lightly, otherwise you are going to struggle in 12th. Next, from vicinal dihalide. So what are vicinal dihalide? Vicinal means in the vicinity. The vicinity means on adjacent carbons. So vicinal means in the vicinity, and you know vicinity English meaning is adjacent. Okay. So vicinal dihalide will be those halides. Obviously, these will be dihalides because if we are talking about vicinal, means on two adjacent carbons there are halogens. So this will be something like this. You have CH2, CH2, and here you have bromine, here you have bromine. Okay. If it is ethane, then it will be like this, CH3, CH3. One hydrogen is replaced here on each by bromine. So that's why it is now vicinal dihalide. When it is reacted with zinc, vicinal dihalides, when reacted with zinc, will produce alkenes. So this CH2, CH2 will be produced CH2 double bond CH2 is alkene. Important reaction we will be using in conversions. CH2, CH2. Okay. So what will happen? These two, these two bromines and this zinc, these three will combine, will produce zinc bromide. Rest will join, CH2, CH2 will join to produce alkene. Keep writing these reactions, and after the class, just give 10 minutes to go through all these reactions. You will be able to recall these questions later on. Okay, reactions later on. Similarly, you have the CH3, CHBr, CH2Br. This is when you get it reacted with zinc, this will produce zinc bromide. Rest of the part, wherever you removed the halides, their double bond will be introduced. So here double bond will be introduced. It will be CH3, CH double bond CH2 plus zinc bromide. Okay. Similarly, you can use other halides also. So from vicinal dihalides, you can produce alkenes. Means two adjacent halogens you can remove by zinc. So write it down. Okay. If you want to remove two adjacent halogens, use zinc. So when we do conversions, you should be able to recall this. Two carbons are there on adjacent, zinc, zinc, zinc. Okay. The reaction is dehalogenation. Why? Because we are removing the halogens. So that's why D means removal of halogens. So dehalogenation. Last method of preparation of alkenes from alcohols by acidic dehydration. Yes, Rohan, fine. Now again, alpha, beta there. So I told you whatever is attached other than carbon and hydrogen, that is of importance. So here OH is attached from by acidic dehydration. So from alcohols, so obviously we have alcohol here, OH is there, alcohol is there. So this OH will decide which carbon is alpha. This will be alpha. It is attached to this carbon. Okay. In presence of a concentrated H2SO4. Okay. In presence of concentrated H2SO4, dehydration takes place. We will be using it very frequently. Again, I am writing it and you should write it. Okay. Concentrated H2SO4 is used for dehydration. That is, it removes H2O molecule. Obviously, there should be H2O molecule present. Here it is. This is H2O molecule, H and OH. So it is very much similar reaction what we talked about, dehydrohalogenation. Okay. So in that case, if you remember, here it was X, chlorine, bromine, or iodine. Okay. And we used alcoholic KOH. You remember that? We used alcoholic KOH. Alcoholic KOH removed hydrogen and halogen. Concentrated H2SO4 will remove hydrogen and hydroxyl group H and OH. That is water molecule. Otherwise, it is very much similar. Okay. So if I say there are 2 electrons here, 2 electrons here, this part will form water and this part will form double bond. Concentrated H2SO4, whenever I ask, if it is obviously alcohol, it will lead to preparation of alkene, dehydration. Water molecule is removed by concentrated H2SO4. Now there is something important which obviously not used extensively in 11. I'm not saying it is not used, it is used, not used extensively in 11. What can happen that with dilute H2SO4, it will be the reverse reaction. So dilute H2SO4 does hydration. Concentrated H2SO4 leads to dehydration, removes H2O. Dilute H2SO4 leads to hydration, opposite. So this H2SO4 should be highly concentrated. So you know the function of alcoholic QH, you know the function of concentrated H2SO4, you know the function of Lindlar's catalyst. In Lindlar's catalyst, you know the function of Poison also. What is Poison? Poison is either quinoline, okay, or PbO2, lead oxide. Okay, those are poisons. Lindlar's catalyst, the catalytic part will be lead and calcium carbonate. You can use lead and barium sulfate as well. Okay, all those things. You can use nickel boride also. Okay, nickel boride also. So just remember these functions, what we are talking about. Okay, what is the function of alcoholic QH? What is the function of concentrated H2SO? For all these things, you should be able to recall. The reaction is an example of acidic dehydration of alcohols. Why we say acidic? Because we are using acid and it is removing the hydrated part. Hydration means H2O, dehydration means removal of H2O by using acid of alcohols. This reaction is an example again of beta elimination. Elimination means from where the hydrogen is removed. Beta elimination means the hydrogen is removed from beta carbon.